Good day, ladies and gentlemen. This is the 13th lecture in the second series of lectures describing the implementation of the RM software for filter design. In this lecture, we will talk about synthesis of all-pass filters, which are approximating constant group delay at low frequency. So the term low pass is added. The structure of the lecture will be naming the project. We will explain how to introduce the design requirements, how to synthesize the transfer function, and then analyzing the properties of the solution and proceed to realization in the form of LC passive circuit, active RC and SC circuit, and digital infinite impulse response realization. So we start the program. Allow for the blocked content, and we will visit the recommended design sequence. It will go this way. So we will first give the name, then we will go to the design requirements, and then we will perform low-pass prototype design, which may be one of these two, Thomson or equi-ripple group delay. After producing this transfer function, we will proceed to the transformation. The transformation, in fact, adds transmission zeros, complex transmission zeros, which are mirrored the poles against the y-axis, against the axis of complex frequencies. So practically there is no transformation, simply adding zeros with the same imaginary value and opposite real value. And then we will proceed to the synthesis. Okay. We will, to simplify and to make the story shorter, we will use the Bessel filters, and here it is, all-pass, low-pass filter design. This explains what is asked. So the first data to be entered is the group delay of the all-pass filter. This is a tricky question since the area under the group delay curve is pi halved multiplied by the order of the filter for the low-pass filter and multiplied by twice the order of the filter for the all-pass filter. So that if we set the group delay, then we are setting the approximating interval. So we will put here 10 microseconds, and we will see what will happen. So the maximum group delay error has no importance because we are going with the maximally flat approximation. Yeah, normalization resistance is 1 kilo, and then that's finished. We proceed now with the transfer function synthesis of maximally flat, that is Thomson. And the program claims that sixth order filter will be satisfactory. We will accept that. And we are ready to produce the low pass prototype. That done, we will go to transformation, meaning that we will add complex transmission zeros. The question is, which transformation should be performed? It is number 4, low pass to all pass. And that's finished. Now we perform the transformation, which is done at once, and we may proceed now to the synthesis. First, we will go for the passive synthesis, for which we have a specific program developed for all passive LC circuits. Its name is Kaskade AP all pass. Done. Now we will see what happened. Here is the spice file. And here is the response. Let's see first the group delay, which is more important. And as you can see, the approximation is about 200 kilohertz constant group delay. As for the amplitude, you can see here microdecibels, which means the unity gain is approximated with at least 7 significant figures in the schematic, not only in the transfer function. Now we will go for the schematic. So it's sixth order, and there are 3 second order cells which are producing complex transmission zeros. As you can see, a transformer is necessary for this to be run. In general, it may happen that a variant with no transformer may be satisfactory, but that is only in general. In fact, practically always one will need a transformer to do such a cell. Okay, now we will go to the Kaskade RC synthesis. Here is the spice file. Again, let's see the group delay. Of course, everything is the same. And again, 0 dB. Here is the structure. And here, these are the cells, active RC cells, which are second order, which are used for the realization of one cell of the second order cell of all-pass circuits. There are 3 of them. A lattice. So this is substitution for the lattice, which was usually used earlier when a circuit without transformer were designed. Now we will go for the RC parallel. Again, here is the SPICE file. Again, about 0 micro decibel and about 200 kilohertz is the approximation interval, and this is the schematic. Now it is parallel. The parallel realization practically uses always the same cells due to the nature of the structure. And this is the summing, and this is the details of the summing. Now we will go to the switched capacitor, 10 megahertz, because the frequency is about 100 kilohertz, so that is the same like earlier. Normalization capacitor, let's be 1 picofarad, and then we will start the synthesis. And then here is the SPICE file. Here we cannot see the attenuation because we are in the time domain. Let's look at the. It's also doubtful whether the anti-aliasing does well, but it does, since its values are accommodated to the passband. Here are the values. You see, these resistors are defining the cutoff frequency of the anti-aliasing circuit. And here is the structure, which is similar to the parallel. RC is the same always, summing and so on and so on. And then we will go for the digital. And here is the program. We will look first to the report. Here are the coefficients, which you can see. These are, you cannot recognize among them whether it is all pass or not, so they are coefficients. But that can be seen in the table which was produced for the Excel. So we will insert a diagram. So this is the phase. This is the phase. Of course, it's linear. This is the gain, it's 1. This is the group delay, which is approximating for almost 200 kilohertz. And this is the logarithmic, the gain in decibel. As you can see, it's practically unity with 10 significant figures. That is the story of all-pass, low-pass synthesis with the use of the RM software. Thank you very much for your attention.